Week 3, this week will be about loss functions and optimization. Remember, the previous week we have talked about the idea of features and how important they are for machine learning. And prior to deep learning, we had this era of machine learning based on pattern recognition, which was the age of handcrafted features. The deep learning revolution was, in a way, learning those features, making your system model to learn those features in a non-transparent way, because we don't know what kind of features deep learning will understand. By the end of the previous lecture, we have talked about the concept of score function. Remember, the model will create a value, which is like the quality of your decision. If it's a classification decision, and if you're trying to classify something in a binary manner, if it is yes or no question, the score function, the model will give you a value. This value, if it is closer to 0 score, then it's going to be like no. And if it's closer to 1, it's going to be like yes. Why 0 and 1? Remember, what we done was called supervised learning. And in supervised learning, we provide those values as labels, as annotations. And when we say no is 0 and yes is 1, the model will try to fit your score function to those values. So a good model will provide you score functions where no will correspond to 0 or closer to 0 values, and 1, yes, will be closer to 1 values. So that was the case. How you could make your model work like that was called training. And training was about optimizing the parameters of your model for this score function. A brief summary of supervised learning. This is machine learning, guys. I mean, remember, machine learning was the higher set and deep learning was the subset. And what we are doing in deep learning is a part of machine learning, is a subset of machine learning. And actually, what we'll be talking about in this course mainly, remember from first week, is supervised machine learning. So there will be labels. We're going to make our model evolve, train, learn, change its parameters, change its weights accordingly, such that the model will provide the proper score function for us. To properly train a score function, we said you need to optimize the weights. To optimize the weights, you need to understand how well that score function works. And we also said that, this is still a summary, where we defined a loss function, which can penalize how good your score function is doing, okay? We have briefly talked about loss functions and optimization. This week, we are going to be talking in more detail. However, the idea of loss functions and optimization is a broad subject, guys. It's a very important part of an introductory level deep learning course. That's why we are spending an entire week for it. However, an entire week is never enough for a subject like optimization and loss functions. After this week, you will have the necessary knowledge to be able to train your simple neural network. I mean, you won't be able to train it hands-on yet, but in a couple of weeks you will. And while you're doing that, the information you need about optimization will be provided here, enough, sufficiently. However, I repeat, optimization and loss functions is a broad subject. There are entire courses for it. I mean, in EE department, there's an optimization course. There are related courses. I strongly recommend them. But in deep learning, we are still using, in introductory level deep learning, a very simple version of optimization, some versions of optimization algorithms, which is based on gradient descent, which we are going to be talking about today. So we're going to be focusing on that. Okay, let us continue with this brief introduction. So the first slide is about what I was trying to say in this 5-minute introduction. We previously talked about feature spaces and score functions. Now we'll talk about ways to create that desired score function, and that way is optimization and using loss functions. We'll talk about the concept of loss function, and loss function will find us the weights, the parameters of the score function, which is basically training your model. Okay, remember score function. You had an input, you had an output. You knew what the output should be, which was the labels, the trademark of supervised learning. And score function was actually a function, which is providing you a value, okay? So you may think of it as a function of input and the parameters, which you can change and tune, provided that score function is y. Remember, score function in some slides are s of score. So I use it interchangeably, try not to, I wish that I didn't do it in slides this way, but try not to confuse it. Okay, so how to find the correct data? That was what we were talking about. So supervised learning is about using the annotated knowledge in a loss function to find those parameters. Simple as that. If you're doing support vector machines or Gaussian mixture models, artificial neural networks, I don't know, any kind of supervised machine learning technique, this is the case. So you are using labeled training data in the training set. So you have the ability to penalize your score function. If you can check if your score function is good or bad by looking at your annotations. In order to mathematically do this, you need a function which will be called the loss function. So loss function will get as input the annotation you get, the score you get for that input, and will give you a penalty. I mean, you did well, you did not do well. According to your doing well or not, you will search the right parameters in a search space. This is basically what optimization is. So in supervised learning, that annotation is conventionally called as ground truth because we believe that it's true. We find our parameters according to that ground truth. In basic supervised learning, it is like the absolute truth for us. But in advanced machine learning, you're going to see that there are things like semi-supervised learning or meta learning or noisy labels, which are beyond the scope of this course. However, in today's world, ground truth is not absolute. So we will have to find in future, in advanced machine learning techniques and deep learning techniques, find ways to properly handle noisy labels or noisy ground truths. Now, we don't do that. We believe that the ground truth is the truth. And for simple problems like classification, this is usually the case. I mean, if you're trying to classify apples and pears, well, it's not a difficult thing because if you've collected the fruit from an apple tree, well, we can say that it's an apple. So for basic problems, the ground truth is absolute, and we are going to assume that it's absolute in this course. So what are annotations? I mean, it could, if you're doing classification, the annotation is the category. This is an apple, this appear. However, we're going to be solving more complex problems like detection in an image or in NLP, again detection, a certain word, a bad word, for example, an animal detection. Someone is swearing in a conversation. You need a detection for that. So when you're detecting something, you're detecting a limited region within the entire signals, whether it's a sentence or a computer vision input like image or video. In that case, the annotations are different. They could be boxes on an image. And when the annotations are different, the type of penalty you're going to create with your function will be different. The penalty function, loss function, will be different for a detection, vision detection problem, which will be a box and your box. You're comparing two boxes. Do they collide? What are their areas? So difficult job. Or if it's classification, is it the same class or same category? Different problems will need different mathematical operators. So the loss function will be decided according to the problem. However, you will also realize that in introductory level deep learning, in a course like this, for these fundamental problems that we're going to study, whether it's classification, segmentation, detection, whatever, there are some certain base functions we always use. For classification, there's a loss function everybody uses. So we are going to be using them off the shelf. Because as I just said, like 10 minutes ago, if we delve into loss functions for different problems, different optimization techniques, well, that would make a course on its own, okay? So I'm going to give you some fundamental loss functions, which are, appropriate for a specific problem, because they are the mostly used loss functions. So I'm going to just get them off the shelf and give it to you, okay? But I'm going to explain why. Good. So depending on the problem type, the character of annotations may differ, just like I said. So how to find the ground truth? This is important, guys, because you're going to be deciding on your projects in a couple of weeks. And since you're going to be most probably doing supervised learning, which I strongly recommend you to do, you're going to be looking for a data set plus a ground truth. So when I say data set, it is not just the data. If you're doing supervised learning, it is the data plus the annotations. So depending on the type of problem you're trying to solve, you will need the type of annotations that is compatible with the problem that you're trying to solve. So there are different, this has become actually, this is important since after deep learning, supervised learning became very powerful, data annotation became a very important sector, a business type. Today, there are even companies, guys, which survive by only doing data annotation in Turkey. I know those companies. Imagine you're a company and you want to solve a problem. You want to automatize some of your process in your factory, I don't know, and you need data. You call that company, just make the annotation. You pay for 20,000 samples, they do the annotation. They give you a guarantee about the annotation. So annotation is an important business. However, you don't have to find a company for that. You just check the internet and you'll find very nice data with annotations. And if you want to create your own problem, however, there are tools to make the annotation. I don't recommend you for this, for this course, because annotating a data set, sufficiently large data set for your problem is a big job, so don't do it. Find that data set with an annotation, okay, for this course. That's mainly about how to find a ground truth. Well, I recommend you find it on the internet. So after this introduction, maybe you're ready to talk about what actually a loss function does and how does it work. The brief lecture that we're going to talk about today about loss functions and optimizations will provide you ways to understand how your training will take place. Because in deep learning, in your first projects you're going to run, you will have to, so to speak, babysit your project. That's how they call it in deep learning world. Babysitting your training. Because while you're training, you just set everything up and you look at the training graphs. What are training graphs we're going to talk about? You need to understand what is going on during training, because you might have to change your things. I shouldn't train it this way. I should train it that way, kind of. To be able to understand that, you need to, roughly understand what the training procedure is all about, how it's getting optimized, how the parameters are going. Are the parameters being updated, how everything is going? So the idea of this week's lecture is to give you a general understanding of how optimization works for types of problems that we are going to deal with. Okay, so loss function. I'll get back to my definition. Remember when I talked about the loss function, it had two inputs, the ground truth and the score function. The score function, the output of the score function. And to get the output of the score function, you need the inputs of the score function. So I define the loss function as input and the ground truth, parameters within the score function. So f being the score function, g being the loss function here. Okay, so whether these parameters are good, the loss function will provide you a smaller value, because loss function is like the cost function in statistics. It's penalizing you. If it is high, then your score function is not doing good. If it is low, that's your score function is good, because it's kind of checking if there is a great difference between the score function and the ground truth. If they are similar, it's giving, so it's like a difference function. Absolute difference, for example, which is called L1 norm, is a type of loss function. You can use it. I've used it for some regression problems previously. Okay, so let's try to mathematically put a value. Let's say that my score function is this. Very simple. You remember from the previous week, the first axis, x1, because I put the axis names as x1 and x2, no x and y, not to confuse you because we are using y as the output of the score function. So these are like the dimensions of the feature space, okay? Remember, as x1 gets larger, it's greenish. And as x2 gets larger, it is spherical. So I'm defining an appleness measure, guys. So 2x2 minus 3x1. So theta is simply, in this case, this vector, because those are the parameters of a score function. If it's a linear model like this, the score function does not have to necessarily be a linear model, because the score function is actually your machine learning model itself. It is providing the result. So the parameters of my machine learning model, which is a linear classifier, just like the previous week, are these values. How did I find these values? Maybe I did pseudo-inversing like the previous week. Maybe I randomly designated them, who cares? This is my score function and my model right now. And these are my parameters then. Because if I matrix multiply this vector with x column vector, I get this value like this, x transpose dot theta. Okay, are they good? Say x is this value. I have an apple which is kind of greenish and which is kind of spherical. I have this value. It's not an appleness measure. Sorry, when I was preparing slides, I remember now. I've designed it as a juiciness measure. Okay, it's a juiciness measure. So I'm saying that when it gets greener, it gets juicier. I don't know why. That's how I define it. Maybe it's not a good function. I'm going to get penalties for it. And when it gets spherical, it gets juicier as well. So okay, so when I say about some, so it is, say x is minus, so it's not greenish, sorry, it's minus 1.5. So it's reddish. And so it's like this. So this apple seems to be this sample, right? So I would say that it's juicy because I mean, it's reddish and it's spherical, I don't know. So I would say that its juiciness measure is 7.5 because of these parameters. The thing is, am I correct? I'll have to calculate the penalty. In order to do this, I had a bunch of apples and pears, and I've collected gourmets from the world because I have incredible amounts of money. And I've asked them to take a bite from each sample and note a juiciness level for me. I've taken the average, and I know the juiciness value for each apple or pear. And for example, the average juiciness level for this sample was decided to be 5.0. Then I would have, if I'm using an absolute difference measure as the loss function, which is also called the L1 norm, I will have a penalty of 2.5. This is loss function, it's simple. The loss function could be of a different kind, more complex function. The model could be different, not a linear model. The parameters could be different. In that case, the loss function value, the output of the loss function will change, of course. But this value will be the value, and this function will be the value that I will try to optimize, argmax or argmin. This is the convention you use in mathematics to optimize a parameter in a function, argmax, argmin. Okay, very good. So if the score function was perfect, it would have given me 5.0. Perfect means compared to the ground truth, because in this example, I'm taking ground truth as absolute. They are the gourmets of the world. How can they be wrong? So what can we change to make this value 5.0? In this model, the only thing we can change are the parameters. So I will find a way to change these parameters, guys. Good. So loss function quantitatively tells us how good or bad the score function does. Usually at start, score functions are bad because you randomly initialize those values. You don't know. Because actually we had two values here and I had an intention of making juiciness as spherical or reddish one. But that doesn't work like that when you're using large deep learning models, because the number of parameters you're going to have, guys, I'm not kidding, hundreds of thousands. You cannot just think of hundreds of thousand parameters as human beings. I mean, you can do it instinctively in your brain because your brain has trillions of parameters which were trained during your entire life, but you had the mechanism to do it. You don't have the capacity to do it, to control it. And we need a mechanism to do it mathematically so that we could imitate it, model it, emulate it in our models. Because we don't do it, we write an algorithm to do it for us, which is called optimization. So, just like I said, I'm going to be providing you loss functions and score functions. The score function will be a deep learning model, because this is a deep learning course. Loss functions according to the problem. And I'm going to define them off the shelf. And you will have many questions. Why am I using this kind of? Well, there are many mathematical discussions about it. For example, classification problem. I'm just defining one. We usually use cross entropy. Maybe you've heard of cross entropy. If you're from statistics, you've heard of that. If you're coming from a different background, maybe you didn't hear about it. I'm going to explain it. There are a lot of whys about it. Why? Well, when I explain cross entropy, it will make sense. It makes sense. But why not another type of one? There are a lot of answers for that, which will be beyond the scope of an introductory level deep learning course. So don't get, frustrated by that. And always remember what Andrew Ng says. Don't worry about it if you don't understand it. It's a bit funny, but these parts are the parts that we should just have a belief on what that guy says. Okay, so score loss function. So cross entropy. Let me briefly talk about cross entropy, guys. I'm sure in your backgrounds you have heard about something called a distribution, a probability distribution. So I'm going to write a probability distribution here. So this is a probability distribution function, okay? This is a PDF, probability distribution function. So you have a value, a random value, a stochastic value, x. I'm using a tilde over it. This is a tilde over it. I'm sorry about that. It can take values between 0 and 5, for example. The values that it can take and 0 and 5 are distributed like this. It shouldn't be like this. It's like this, but I'm terrible at using this pen. So sorry. So it's like this. And in a PDF, this is a probability distribution function. So this is the probability of x actually. If you take the integral of a probability distribution function, it will add up to 1, which means the total possibility of x having these values is 1. So it means that it cannot take any value except 0 and 5. So this is probability distribution function. Now I'm going to be talking about a discrete probability distribution function. The famous example is the backgammon dice, which can take values from, this is 0, values 1, 2, 3, 4, 5, and 6. This is a discrete probability function. Each of them making 1 over 6 because the discrete sum, this time not the integral, the discrete sum of the possible values should add up to 1. Because when you throw a dice, at backgammon dice, you cannot get a single one. So this is discrete probability distribution. Why did we define this? Because the result of a classification function is, a discrete distribution for us. Well, I'm asking, it's an apple or pear? Well, it's a yes or no question, but it's a two-class classification problem. So even if it is, even if you can decide it, the answer should be a probability distribution function. So it is apple or pear. So if you're sure about that, so yeah. So it is 1 and 0. So this is an answer to that question. So I would want my score function to provide a value like this because it's a decision. I could do it differently, like getting an appleless measure. But when you get an appleless measure, like it looks like an apple, it is actually a regression problem. In a classification problem, what we usually want is a distribution, because when you have other types of classes, for example, in AlexNet, we are going to see, AlexNet will classify an image into 1,000 categories. it will be a 1,000 sample discrete distribution function having probabilities out of that 1,000 categories. Okay, so the score function should be a discrete probability distribution for a classification problem. So I need a score function which can create that for me. Softmax, which we are going to be talking about in the next slide, is a type of function which can convert those type of scores, that real value scores, multiple scores, into probability distributions, discrete probability distributions. Well, good. So I know that for a classification problem, I need a discrete probability distribution. Good. What about the loss function? The loss function was trying to understand if the output of the score function was good enough compared to the ground truth. I've decided that the score function should be a discrete probability distribution. Then if I'm going to compare it to a ground truth, they should be of the same thing. Then the ground truth should be a discrete probability function too. So I would say that in an apples and pears problem, the ground truth should be a discrete probability function, a very simple one, where for apples, it is 1, 0. For pears, it is 0, 1. Just like the previous week example. Now I have the ground truth as discrete probability functions. I have the score function as discrete probability functions. We are talking about classification functions now. I need a difference between them. In mathematics, in statistics, there are a lot of ways to compare two probability discrete distribution functions. And one of them is called the cross entropy. This is a function which gives you a similarity between two discrete probability functions. So that's the loss function. So if it is 0, they are the same probability. If it is infinite, they have no relation, no correlation, nothing at all. So that's how cross entropy works. So without delving into more details about cross entropy and soft function, I'm going to talk about how I use them. Okay, good. So I'm going to jump from the apples pears example to a vision problem, so that this will give us another perspective about how it should be done. So softmax is a score function normalizer. It's why it's called a score function normalizer. Imagine your model is a linear model. It provides you values about being apple and being pear, just like the linear classifier we had. So is it an apple? Yes, it is 5.1 apple. Is it a pear? It's a 2.1 pear. Well, I can understand that it is more probably than an apple, but I need a probability distribution function for that. So if you have values for different categories, softmax can convert them to a normalized distribution, because when we say normalized, we are trying to say that the sum will add up to 1, which is the thing that you need to have when you have a discrete probability distribution function. Okay, so it converts real value scores to probabilities which sum up to 1. So PDF, discrete PDF. So imagine I have an image and I have a model. I have 3 categories, say. So the first category says 3.2. The second category says 5.1, which is working, and probably model is not correct right now. And minus 1.7, they could be negative values. I need a probability for that. So what I do is, this is the softmax function. You take the exponents first, so that the negative values, the idea of softmax is, your negative values become positive again. Then you sum them up and normalize them. So in this case, it is like almost 0% frog, 13% cat, and 87% car, with respect to these values and the softmax function. So now thanks to softmax function, it provided a distribution function to my linear classifier, if it was a linear classifier. You have seen linear classifiers, that's why I'm going over that example. So cross entropy distance, loss, cost. I mean, in different fields of science, they use different words. I mean, people use cost usually in economics and loss in AI and distance in signal processing, but they're quite the same thing in our way of seeing things. Cross entropy is commonly used in machine learning as a loss function for classification problems. It's a measure of, from the information theory, which can find the distance between two distribution functions. And so you have a score of, for example, 4 classes in this example. And you know that from the ground truth that it is only 1. You get the distance between these guys. According to this distance, we're going to decide if the score function is doing correct or not. Good. Any questions up to now about score functions, loss functions, and etc.? The only score function and loss function you've seen was about classification, about regression and other problems we are going to talk about. Any questions until now? Good, I think. It doesn't have any meaning. Your friend's asking, if you haven't here, the Zoom people, the value, the score value of frog being minus 1.7, does it have a meaning? Well, we don't know what the model is. The model is, it could be a linear function. It could be a neural network, I don't know. It is doing some mathematical calculations and it's providing this value. And that mathematical model, since it has parameters, can be of any parameters. And there is nothing that can stop it to provide negative values. So think of negative values as real values from minus infinity to plus infinity. Score value could be anything. It doesn't mean anything. But what we want, what we push the model to do in this case is, we want the score of the correct category to be larger than the others. Negative, positive, we don't care. Larger. That's what softmax does. Okay. So being negative does not necessarily mean anything. So a good example is, let's add a value to all of these. Sorry, let's add. Let me get my pen. Terrible pen. So I'm adding 1.7 to all of them. In this case, this is going to be 4.9. This is going to be 6.8, and it's going to be 0. If you calculate the softmax function, you'll get something very similar. So it doesn't necessarily mean anything for this very simple example. So actually, your question touches to a point which means, what should the score functions be for a classification problem? We don't care. What we want is to model to properly fit to a score function and the loss function, properly training it so that we get the right category. We don't care. Maybe you train AlexNet for once, you have an accuracy of 99%. You train AlexNet with some random changes. It again gets the same results, accuracy results, but this time score functions are maybe slightly different. We don't care. Mm-hmm. Well, actually, the reason we normalize the score function is to convert the results of the score function to a discrete probability distribution. Okay, at this point, we have a score function that, we are adding softmax to our model so that the entire model, the model plus the softmax, will create a score, which is a discrete probability distribution function, because this is a classification problem. Now, about the loss function. Loss function is the distance between your score and what it should be. And for a classification problem, what it should be is some discrete probabilities where the correct category is 1, the others are 0. You calculate the distance. At this point, your question, do we normalize this value? Definitely not. Because if it is wrong, I need to see how wrong it is. If it is, cross entropy will provide you values from 0 to infinity. So if it is towards infinity, then it's very wrong, correct it. If it is 1,000, correct it a bit. If it is 500, correct it more. If it is 250, 100, I'm changing the values. Correct it more until it becomes 0. It never becomes 0, but so we never do that. That value, that distance is very important for us. Okay? Just like I said, I'm talking about the fundamental concept of optimization. And if you're very new in this stuff, it will take some time to, I mean, before the ideas will fit properly in your head. But it's there, simple ideas that you can easily catch. Don't worry about it. Don't worry about it if you don't understand. Okay, so let me continue.
Hocam bir şey sorabilir miyim?
Please.
Yani burada bütün amacımız raw data'yı probability'ye çevirmek değil mi? Temel amaç.
For classification, yes. Not what your friend is asking is, our entire purpose here is to convert raw data to probability. Well, yes, the answer is yes, but to properly and in more detail, to put it in more detail, for a classification problem, we have the raw data, raw signals, image, whatever. We need a score function which will provide us a probability distribution. And yes, what you say and what I said just overlaps. Okay? Answer to your question?
Yes.
Okay, so we have a loss function. It can analyze what our score function does. And our score function is not doing correct. We will need to change the parameters of the score function to get that value properly. This is called optimization. Optimization is an iterative process to find the correct parameters for a given cost function, loss function, whatever it's called. Okay, so by changing the model parameters and iteratively checking if your model is doing, you find the correct parameters. This is optimization. Optimization is a broader definition, of course. Every problem, I mean, optimization guys, mostly control engineering guys, they always say every engineering problem can be modeled as an optimization problem. That's what they usually say. So optimization is a broad title, but in our case, this is simply this. We have a model, score function. We'll try to find the correct parameters of the score function. That's the idea. Okay, how to do it? Well, there are many methods. And believe me, even random search is a method. But it doesn't work for deep learning models. So why random search is a bad idea? I mean, because when you randomly search the entire space, you can find it, and there's nothing stopping you from finding it. First thing is, it takes too long, because the parameter space we have will be hundreds of thousands of dimensions. So it won't be like the peer settlement measure, guys. It was the peer settlement measures. Yeah, look for the best apple or pear in the world and eat it. Well, you'll have the problem. But in deep learning, the parameters we'll have will be extreme. So there's no way you can search that space. And actually, there's no strategy. I mean, we are intelligent beings. We can come up with strategies. And we know mathematics, we know calculus, we know linear algebra. And there are very simple strategies for that. We can apply them. And frankly, the optimization strategy we generally use at this level of deep learning is one of the simplest strategies of optimization, which is the gradient descent. And it works. I mean, until something better comes up, it works. So let's see what that strategy is. Experience shows that it doesn't work when the parameter space is vast. Okay. It is simply gradient descent is simply following the slope. I always, if you're new to optimization, most of you are not, but if you're new to optimization, I always resemble gradient descent as a blind guy trying to find its way in a valley. So you're a blind person, you're in a valley, you are trying to find a plateau, which is, I mean, compared to where you are, have lower altitudes. But you're blind. Because if you weren't blind, you would just check the space. You cannot do that. You're blind. The only thing you can do is you can feel the slope. So feeling the slope. What would you do is you follow the slope. Will you be able to find, depending on the, geometry of the place, it's not geography of the place, you may end up in a place where you think it is the best place to end up, but it is probably not, which is called in optimization the local minima. So whenever you try to understand what gradient descent is doing, is you are the blind guy trying to find its way in a valley, and your way is to the lower ground. Simple as that. So what you do is you do it iteratively, right? You're the blind guy, you take a step and you try to feel the slope. You take a step, try to feel the slope, take a step. Sometimes if you're a clever guy, you are, when you feel that it's, I mean, imagine you're blind, but you know that there's nowhere you can just bump into, for example. If it is the, if it's a plateau, you may try to run so that to make the search quicker, right? But if it is very steep, well, you would have small steps to find your way. Strategies. So, so what you're trying to do is to find that decreasing trend in the slope. This is a mathematical definition, guys. In a multi-dimensional space, if you're trying to find the slope, that's called the gradient, okay? The gradient is the way upwards, so you're trying to find the negative gradient. So you search for the negative gradient. And it's a very simple iterative function, which is the function of the gradient descent. Okay, it's like a blind man, you're like blind walking around in an n-dimensional field, feeling the slope, following it. I mean, if you're a blind man walking in a field, it would have been a three-dimensional field, but in our case, it's an n-dimensional field, and n is extreme. Okay, so before we get to the functional derivation, let's remember the very simple rule of, before we get to the function of gradient descent, let's remember the very simple rule of derivation from calculus. So this is how you calculate the derivative. So if h goes to 0, this is asymptotically the theoretical derivation at that point. But in order to be able to calculate this, you need the analytical function. So you need that surface to be written like an explicit function, x squared plus y squared. You don't have that. You are the blind guy. If you could see, maybe you could have an analytical function, then you would calculate the best position and jump there. Call it cap and get me there. You are the blind guy. Blind guy phenomenon is trying to tell you that you don't have the mathematical analytical function explicitly. The only thing you can have is feeling the slope. You can calculate the slope at some point. How to calculate the slope at one point? Well, you can calculate the slope by different ways. So numerically, you can calculate the slope. I mean, you could take a step. If you take a long step, it will have more error. If you take a smaller step, it will have a smaller error. You remember the derivation when it goes to 0, that's theoretically the best derivation you can get. So that's how the blind man would do is try to get the steps simpler and simpler. Okay, in multiple dimensions, the gradient is actually, if you want to imagine it, is the vector of partial derivatives along every dimension. Because, for example, in 3D world, let me write, sorry. Arkadaşlar, durdu değil mi şey? Sorry. Share screen durdu. Okay. Okay, you can see the screen right now.
Yes.
Okay, you can. Sorry about that. Okay, so in a three-dimensional space, the gradient is the partial derivative with respect to the x, y, and z dimensions. Okay, so so for the blind man example, you are taking the partial derivative of the altitude. So let me say altitude. The altitude, because that's what the blind man is trying to do. But in the real world, it's going to be the loss function versus the parameter space. So altitude will be the loss function. X, Y, Z coordinates of the blind guy will be the parameters of the score function. Okay, so it's going to be a vector. We're going to get there. So the slope in any direction is the dot product of that direction with the gradient. So how to calculate the slope? What you do is that gradient function, let's say gradient function. I shouldn't have deleted it. dy dz. So this is the gradient function. Dot producted, which means you can just transpose times the dot product direction with the gradient dot product of direction with the gradient of the steepest descent. So if you want to find the gradient in one direction, you get a direction, the x direction, and calculate it, you get the gradient. okay, in one direction. That's the mathematical definition of it. So how am I going to use it? Very simple, actually. Okay, so what we do is, what the blind man does is, it's feeling the slope with its steps. Okay, guys, this is the step size, lambda. Okay, no, it's not the step. Yes, it's the step size. This is the felt slope, the slope you're feeling right now, which is the derivative, the partial derivative, with respect to every parameter in your score function. Okay, so this is where I am as the blind guy, and this is where I will be next time. So I'm standing at somewhere. I take a step of, I don't know, 1 meter, a long step. This was the slope I felt. So the slope you felt, mathematically, gradient is in the positive direction. That's why I'm using a negative sign here, because I want to follow the downward slope. And I get to a new point. I repeat it, I iteratively find this function until I find a plateau. This is called the gradient descent. So lambda is the step size of the blind man. It is also called the learning rate, because if I take 2 big jumps, I would just go further, because what I'm trying to do is trying to learn the parameters for the blind man to reach the place. So it's the going speed is learning rate for your problem. Is getting larger steps a good thing? Well, you may think that higher learning rate is a good thing. Not necessarily, guys, because when you're making giant steps, maybe you are missing things. Maybe there was some slope downwards you skipped, and maybe you could find a better place if you just had smaller steps. But when you're doing very smaller steps, well, the blind man will go, I don't know, hungry and die before he finds the plateau. So this is a trade-off parameter which we are going to be dealing with in our trainings. Okay, any questions about the gradient descent?
Hocam şu new dediğiniz şey float mu oluyor? New volt yazdığınız şeyde.
Float, you mean? What is a float?
Yok, slope mu oluyor? Eğim mi oluyor yani new volt yazdığınız şeyde?
No, it's the place of the guy. Slope is this. Let me write it. So the good question. Your friend is asking if theta is the float. So I'll start with the blind man analogy, then I'm going to get to the model. Guys, this is by definition the slope. The slope. Slope. This is by definition the step size. This is the location of the guy. Location. And this is the location new. So it is like I'm here, I'm taking a step of this size along the slope direction, and I'm now here.
L fonksiyonu ne oluyordu peki?
Sorry, L is the loss. L is like
Loss
the
function.
altitude in our case, altitude. If trying to make the same analogy, because we are trying to find the partial derivative of the altitude to x, y, z three-dimensional world coordinates, that's giving us the slope. Okay? Answer to your question, I hope. This may be confusing at the start, but so let's get to our world now. These are my parameters of the model, and these parameters create the value. That value is where I am at that space where that old guy is. I'm trying to get to a better place, lower altitudes. In this case, it's lower loss, where my parameters will create similar results to my ground truth. So I take the partial derivative of the loss with respect to these parameters. That's the gradient, but in the forward direction. With my step size, I subtract it. I'm in a newer place. My new parameters. It's a better place for me, because this place mathematically create new theta will mathematically create score values which are more similar to my ground truth. That's the gradient descent. Hope answered your question. Doruk. Okay, any other questions?
Ben de